Hi, this is Ms. Fitzmaurice. This video is an explanation of the problem, the 2008 problem, which we tried in class today. So this is on page 3 of your Unit 8 packet. And the first thing that we have to do in this problem is we have to draw a diagram labeling all of the forces acting on our rod. Okay, so we know that the rod has the force of gravity acting on it, and we draw the force of gravity from the center of the rod's mass. Okay, so this will be mg going down. It also has a weight, so we're going to have mg from the weight, and just so we're clear throughout the problem, I'm going to call the rod 1 and the weight 2. So I have m1g and m2g. I also have tension from this string that's acting on the rod, and since it's not moving, I know sigma fx equals 0 and sigma fy equals 0. What that tells me is that in both the x and y direction, I need to have a force at this hinge that is canceling out. So the force at my hinge cancels out my x part of my tension force, and it also cancels out my 2 mg's. Okay, so these will be my forces. In part B, I want to know the reading on the spring scale. Since the spring is connected to my rope, I'm really asking for tension. And so to find that, I can use the fact that this thing is in rotational equilibrium, so sigma tau is equal to 0. Okay, now I'm looking for tension. And when I find tau, when I find torque, I have to pick a pivot point. I could put it really anywhere on this rod, and it would still be technically correct, and I could get to the same right answer. So I could put it there, or here, or here. But I want to think about what's going to be most mathematically useful. Now I want to find tension at the end, so I don't want to put the pivot point right here, because then my radius for tension would be 0, and the torque for tension would be 0. So I'm not going to put my pivot point right there. However, it would be useful to put my pivot point right here, because then the radius between, the distance between my pivot and FH would be 0, and FH will be canceled out. Okay, so I'm going to put my pivot point right there, and then I'm counting up whether the torques are positive, negative, or 0. Okay, the torque for FH will be 0 because the radius, the distance between my pivot point and FH is 0. Okay, M1G will make a negative torque, M2G will also make a negative torque, and tension will make a positive torque. Okay, so now I have to write out the individual torques. So I have the torque of the tension, which is positive, minus torque, I'll call that torque 1 for M1G and torque 2, and I set that equal to 0. And then I'm going to plug in my equation for torque, so that's T, and I'm just going to put RT sine theta T minus M1G R1 sine theta 1 minus M2G R2 sine theta 2. And I set that equal to 0. Now I know I'm going to call the length of my rod L. I have a number for it, but I'm going to stick to variables until the end. Okay, so I know that the radius for T okay, because it's L away from my pivot point, will just be L. Actually, I'm going to write that in black. So I have T times L. My angle is given to us, that's 30 degrees, so sine 30, TL sine 30, minus M1 G, and then my radius for M1, the distance from M1 to my pivot will be L over 2, so I have L over 2, and then my angle is 90, so I have sine 90, which is 1, minus M2 G, my radius from my pivot point to M2 is the whole length, so I put in L, and then again I have a 90-degree angle, so sine 90 is 1. Okay, and I notice that every single one of my terms has an L in it, so I can cancel out my L's. And I also know that sine 30 is equal to 1/2. Okay, so I'm going to rewrite this equation on the next page, but I'm going to keep in mind that I got rid of my L's and that sine 30 is 1/2. Okay, so this is my simplified equation. And I'm going to solve for t. I'm going to bring all of this to the other side and multiply by 2. So I have t is equal to g times, I'm multiplying the whole thing by 2 to get rid of this 1/2. So g times 2 m1 over 2 plus m2. And I know that m1 is 2 kilograms. So I have t is equal to g, which is 10, times 2 times 2 over 2 plus 0.5. And so I have 20 times 1.5, which is equal to 30 newtons. Okay, so we have T equals 30 newtons. In part C, I want to find the rotational inertia of the rod block system around its hinge. And the angular inertia, I total, is just going to be the sum of all my individual I's. And so if I look at this picture, I have this hinge, right? And I have a block hanging off of it. So my total will be I rod plus I block. And we're going to treat our block as a point mass. And I'm going to still stick to block has M2 and rod has M1. So I have I total is equal to I rod plus I block. I block is like a point mass, so that will be M2 times R squared, but the R will be the length of the rod, so M2L squared. Now for the rod, we know this, if our rod was rotated around its center, I rod, I'm going to say A is equal to 1/12 M L squared. Okay, but we're not asking about moving it around its center. We want to know around this hinge. Okay, so I rod will be, or the moment of inertia, I rod B, which is the actual one we want to use, will be equal to 1/12 ML squared plus, remember the parallel axis theorem, M1 and then d squared, where d is the distance we've moved the axis, so that's L over 2 squared. Okay, so we essentially have I total is equal to, I'm going to move this over a little bit, I rod plus I block. I rod is going to be 1/12 m1 L squared plus 1/4 m1 L squared plus m2 L squared. 1/12 plus 1/4 is the same as 1/12 plus 3/12, and so we get 1/3 m1 L squared plus m2 L squared. I'm going to factor out the L squareds, so I have L squared 1/2 m1 plus m2. Okay, I know that L squared is, or that L is 0.6, so I have 0.6 squared times, and this should be 1/3. I apologize. 1/3, because 1/12 plus 1/4 is 1/3. 1/3 of 2, so that's 2/3 plus 1/2, and we end up with 0.42 kilograms meters squared. Alright, so D says, finally, if the cord that supports is cut, so this cord does not exist anymore, what will the initial angular acceleration of this thing be? Okay, so we're going to use this idea that sigma tau equals I alpha, and we just calculated I, so that was 0.42. So we have I, and we can calculate sigma tau. The only thing is we get rid of the tension. Okay, and the other thing is, because it says about the hinge, so what will its acceleration about the hinge be? We need to use this as our pivot point. Okay, so we have, again, we have m1g, and from the box we have m2g, and the tension is gone. We also have F hinge, but again, because the radius between our hinge and F hinge is 0, our torque will be 0. Okay, so we have to calculate our torque. Both of these torques will be negative. And so we have minus torque 1 minus torque 2 equals I alpha. Again, I'm going to wait to plug in any numbers till the end. So we have minus m1g. Again, the radius for m1 is L over 2. So m1g times L over 2 minus m2g times L equals I alpha. Okay, and I'm going to solve for alpha, and I'm skipping a couple of algebra steps. You probably want to convince yourself that what I'm saying is true, but alpha will be equal to g, or negative g, divided by I, m1 over 2 plus m2. Okay, so now we can start to plug in numbers. We know that we have negative 10, our length is 0.6, our A is 0.42, and then m1 is 2 kilograms, so m1 over 2 is 1 plus 0.5. And we end up with alpha is equal to negative 21.43 radians per second squared.